Welcome to the Deep Dive. We're here to plunge into complex topics and really bring you the essential insights you need. Today, we're tackling something absolutely fundamental, something behind almost everything digital we do: software testing.
Hmm.
Think about it, your phone apps, websites you browse, every smooth interaction. That's thanks to some really rigorous testing. Our source material is this great interview compendium, actually. It gives a unique, very practical look at how software quality gets done in the real world. So our mission today: cut through the jargon, pull out the key nuggets, and give you a shortcut to understanding all that meticulous effort behind the scenes.
Exactly. And, this deep dive, it should really pull back the curtain on all those layers of work that go into reliable software. You'll probably have a few aha moments, hopefully,
Yeah.
about why things sometimes go wrong. And more importantly, how testers are really working to stop those issues before they ever reach you.
Okay, great. So let's unpack this right away then. For many of us, maybe we think of software development as just, writing code. Where does testing even fit into that grand scheme? When does it start?
Well, that's a key point. It's fascinating because testing isn't really an afterthought.
Yeah.
It's not something you just bolt on at the end. It's actually a core part of the software development life cycle, the SDLC. That's the whole systematic process for building software. It ensures quality, correctness, that it meets customer expectations, and all within hopefully predefined time and cost. Think of it like the complete roadmap for creating software.
That makes a lot of sense. So the SDLC is the whole journey. Is testing then like a separate journey within that? Or are they the same thing?
That's a really crucial distinction to make. The STLC, that's the big umbrella. It includes everything: requirement gathering, design, development, and yes, testing is in there too. You've got business analysts defining requirements, dev teams creating designs. But then you have the software testing lifecycle, the STLC. Its focus is only testing. That's the QA team analyzing requirements specifically to build test plans and then actually running those functional and non-functional tests. So yeah, it's like a dedicated testing roadmap, a sort of specialized expedition inside the bigger SDLC journey.
I see. Okay, so once a team starts building, what are the different checkpoints the stages software goes through for testing? Are there different levels?
Absolutely.
Yeah.
Software generally moves through 4 distinct test levels, and each one kind of builds on the last. It starts small. Unit testing or component testing, program testing, module testing, lots of names for it. Basically checking individual bits of code, the smallest functional parts, in isolation. The idea is to catch errors really early.
Right, find them before they get complicated.
Exactly. Then comes integration testing. This is where you combine those individual components and test how they interact. This is super important because, a unit might work fine alone, but maybe a hidden bug only pops up when 2 integrated parts talk to each other unexpectedly. Each stage needs a different focus.
Okay.
After that, you've got system testing. This looks at the entire computer system as a whole, all the modules together, both functional and structural aspects. This is where you really verify the complete system against the requirements you started with.
And the last one?
The final stage is acceptance testing. And this one is maybe the most crucial from like a user's perspective. It's done by the actual end users or the clients themselves. They verify the system before it goes live. It's basically their final sign-off.
Okay. I often hear these two terms that sound similar: checking if something is built right versus checking if the right thing is built. How do those concepts, verification and validation, I think they're called, fit in?
Yeah, verification and validation. They're really fundamental pillars for quality assurance. So verification is asking, are we developing the product accordingly? Or are we building the product right? It's a static analysis technique. That means you do it without actually running the code. Think of it like checking blueprints or recipes. Are the documents okay? Are the designs consistent? You're doing code reviews, inspections, walkthroughs. It's all about checking if you're building the product correctly, following the plan.
Okay, static analysis, checking the plan.
Right. Then validation asks, does the specification really capture what the customer needs? And does the final product actually meet those needs, or are we building the right product? This is dynamic. It does need code execution. It covers all that functional and non-functional testing that we just mentioned. So it's about checking if you're building the correct thing for the customer. One's about process, the other's about the end result's fitness.
Got it. Verification is process, validation is product fit. So with all these levels and checks, how does a team actually plan the whole testing effort? Is there like a master plan doc?
Exactly. There's usually a test strategy. It's a high-level document, often static, usually put together by the project manager. It outlines the overall approach to testing, how to achieve the quality goals, and it's generally derived straight from the business requirement specifications, the BRS. But a good test strategy isn't just documentation. It should anticipate risks, potential bottlenecks. It helps shape resource allocation, maybe even project timelines. It's where you can save a lot of pain later on.
Makes sense. Part of that strategy must be how you write the actual tests, right?
Absolutely. And there are best practices for writing test cases. A big one is writing them from the end user's point of view. Keep the steps simple, easy to follow. Make them reusable if possible. You also need to set a priority for each case and clearly describe everything. The case itself, the data needed, what you expect to happen, any preconditions, post-conditions. A common mistake is mixing valid and invalid tests. It's better to write test cases for invalid inputs separately. Use good naming conventions too. And critically, test cases aren't static. They need reviewing, updating, software changes, so tests have to adapt.
That sounds like a ton of meticulous documentation and tracking. Beyond the strategy, what other key documents or processes keep everything organized?
Oh yeah, robust documentation is key. One really essential tool is the Requirement Traceability Matrix, or RTM. Think of it like a big cross-reference table. It tracks every requirement through the testing process. It ensures nothing gets missed, and you can always trace a test result back to the original requirement it covers.
Okay, traceability, very important.
Definitely. Then you have test deliverables. These are all the things produced during testing tools, documents, components, things like test plans and designs before testing, execution logs during, defect reports after, everything that supports the process. At the very end of a cycle, there's usually a test closure document. It summarizes everything. Tests run, bugs fixed, analysis of those bugs, plus aggregate numbers, tests executed, any bugs still outstanding or rejected. It's like the final report card for that testing phase.
Right. And how do you know when you're actually done with a phase?
That's defined by exit criteria. These are specific pre-agreed conditions that must be met, like maybe 95% of critical tests must pass, or there can be thorough outstanding critical bugs. Once you hit those criteria, you can exit the phase. And underpinning a lot of this is configuration management. It's about maintaining consistency, keeping track of the product's physical, performance, functional, design info, making sure everyone's working on the same version of the software, crucial for efficiency and avoiding chaos.
It's clear there are very structured ways to do this. Are there also different, overall development philosophies that change how this all plays out?
Yeah, definitely different models exist. You might hear about the Big Bang model, for example. It's kind of an older approach, less common now for big projects, very little upfront planning. Requirements are sort of implemented as they come up. It might work for really small, maybe experimental projects or tiny teams, but it can get chaotic fast otherwise.
I can imagine.
And then, once the software is ready, getting it out to users also has strategies. You might do a pilot with a small user group first, or gradual implementation, rolling out features slowly. Phased implementation is similar, but maybe rolling out module by module, or parallel implementation, where the old and new systems run side by side for a while. And even within the testing process itself, you have things like formal review phases that structure the quality checks. Planning, kickoff, prep, the review meeting, rework, follow-up. It's all quite formalized.
It's truly amazing to think that every app or website we use has likely gone through some version of these steps. Understanding these foundations really gives you a framework for appreciating software quality, doesn't it? It makes you see those smooth digital experiences differently. Okay, so we've mapped out the blueprint, the theory of how testing should work. But the real magic, maybe the detective work, happens when testers actually get their hands dirty. So let's shift from the what to the how. How do testers do this work? What are the hands-on methods in their arsenal?
Right, this is where it gets really practical and I think quite interesting. There are essentially three main approaches, methodologically speaking. First, black box testing. Here, the tester acts just like an end user would. They only work with the requirements, the specifications. They have zero knowledge of the internal code or structure. They just put data in, check the output. Like testing a literal black box possessional, you don't care what's inside, just if it does what it promises.
Okay, user perspective only.
Exactly. Second is white box testing. This is the complete opposite. Here, the tester does have access. They can see the internal paths, the code structure, the software's guts, basically. This lets them examine the logic, test specific code paths, make sure internal stuff is working correctly.
So much more technical.
Definitely. And then there's gray box testing, which is, as the name suggests, kind of a mix, a pragmatic blend. The tester has some access maybe to design documents or limited code knowledge. This allows them to create more informed, maybe more targeted test cases than pure black box, but without needing the deep code dive of white box. It's often about finding that useful middle ground.
That makes sense. Knowing some internals could definitely help focus the effort. What about more specific techniques they use day to day? This interview compendium must have some cool examples.
Oh, it absolutely does. Let's look at a few ways they actually dive in. You've got things like random testing, or sometimes called ad hoc testing. It's unplanned. You don't follow specific test cases, you just sort of poke around randomly, looking for defects. It can be good for finding obvious issues quickly, maybe early on.
Like just exploring the app?
Kinda, yeah.
Yeah.
Then there's data-driven testing. This is super important for efficiency. It means running the same test script over and over, but using different sets of data each time. You pull that data from external sources, like an Excel file or a database. Really valuable for apps that handle lots of varied inputs.
Okay, reusing scripts with different data. Smart.
Very. Then, a more precise technique, boundary value analysis. See, errors often happen right at the edges of valid input ranges. Like if a field accepts numbers 1 to 100, errors might work at 0, 1, 100, 101. So this technique specifically tests those boundary values, the minimum, maximum, just inside, just outside, not just random values within the range.
Focusing on the tricky spots.
Exactly. For security and robustness, testers might use fuzz testing. This is about finding coding errors, security holes, by deliberately throwing random, often malformed data at the system, trying to make it crash. If it does crash, a tool called a fuzz tester helps figure out why. It's like stress testing with junk data.
Throwing the kitchen sink at it.
Okay.
I can see how that would find some vulnerabilities. What about testing focused more on, say, performance or the user experience itself?
Oh, absolutely. For performance, there's baseline testing. You run a series of tests to collect performance data, establishing a baseline for how the application currently performs. Then later, when changes are made, you can run the tests again and compare against that baseline to make sure performance hasn't gotten worse.
Okay, measuring performance over time.
Right. And for user experience, bucket testing, or A/B testing, as it's often called, is huge, especially on the web. It's about studying the impact of different designs or features. You show version A of a page to some users, version B to others simultaneously. Then you measure the difference. Click rates, engagement, signups, whatever. It helps teams make data-driven choices about what works best for actual users.
A/B testing. I've heard of that.
Very common. And for checking the application's flow, how it moves between different modes, state transition testing is really useful. It designs tests based on applications that have distinct states or require specific transitions. It's key when the same input might give you a different output depending on what state the system was in before that input, making sure all those transitions work correctly.
Wow, that's an incredibly diverse toolkit. Just hearing about these makes me appreciate the variety of ways testers have to think. What are some testing applications that maybe most of us rely on constantly without even realizing it?
Oh, good question. Well, for anything web-based, cross-browser testing is absolutely essential. This is making sure web apps work properly across all the different browser and operating system combinations people use. Chrome on Windows, Firefox on Mac, Safari on your iPhone, Edge, the list goes on. Without this, websites would just be broken for tons of users.
Yeah, that would be frustrating.
Totally. Another thing you probably encounter is client-side validation. You know when you fill out a web form, and it immediately tells you if you missed a field or entered an invalid email before you even hit submit.
Oh yeah, instantly.
That's client-side validation. It checks your input right there in the browser without needing to talk to the server first. It makes the experience much faster and smoother for you. And from a security angle, testers are constantly probing for web testing security problems. Things like, can they launch a denial of service attack? Can they somehow see another user's data? Buffer overflows. Can they bypass security by typing weird URLs? They're actively trying to break in, essentially, to find weaknesses before malicious actors do.
That's reassuring, actually. So with the sheer variety, I have to ask again, what does this all mean for us, the users? How does it directly benefit our experience?
Well, it leads directly to things like usability testing, especially in web testing. This focuses on how easily you, the end user, can actually use the application. Can you figure it out without needing a manual or programming skills? It's all about making software intuitive, efficient, pleasant to use. That smooth experience you value. Usability testing is a big part of that.
Right, making it easy to use.
Exactly. Then there's globalization testing. This ensures software can adapt to different languages, regions, currencies, date formats, etc., without needing fundamental code changes. That's why you can often just switch an app's language setting and everything adjusts. That takes specific testing.
Hmm.
And of course, GUI testing. Graphical user interface testing. This focuses purely on what you see and interact with, the buttons, menus, text boxes, images. It checks that the interface matches the designs, that everything looks right and functions correctly. If a button is misplaced or text doesn't fit, GUI testing should catch it.
So it looks right and works right on the screen.
Precisely. Preventing those visual glitches and frustrations for you.
Okay, this is where it gets really interesting for me. You're testing, you're finding these issues. Bugs. How are they handled? Is it just fix it? Or is there a whole process?
Oh, there's absolutely a whole process. It's not just random fixes. Every single bug or defect has a distinct bug lifecycle or defect lifecycle it has to go through. And this cycle isn't arbitrary. It depends on the tools the team uses, things like JRA, Bugzilla, Quality Center, and their own internal processes. It's a formalized journey from discovery to resolution.
A life cycle. Okay, so when a bug is found, what information gets logged? What do they track?
Good question. A detailed defect report or bug report is created. It's crucial. Key components usually include project name, module name, where it was found, a unique defect ID, a clear name or title for the defect. Also, critically, a screenshot, steps to reproduce it, the severity, how bad is the impact, and priority, how urgently does it need fixing, and eventually who fixed it and when. This report is the main communication tool. It helps everyone understand the issue, reproduce it, and track its fix.
Severity and priority. So bugs aren't all treated equally. They have different personalities.
Exactly. They vary hugely in impact. You have latent defects, for instance. These are hidden flaws. They might sit there undetected until some very specific condition or event triggers them, like little time bombs.
Yikes.
Yeah. Then there's defect cascading. This is a tricky one. One defect actually triggers other defects later on, maybe in different parts of the application. A real chain reaction. And in terms of impact, you have critical bugs. These mean a major piece of functionality is just broken. There's no workaround. It might block other testing entirely. Huge impact on the customer's business. Similar, maybe even worse, is a showstopper defect. This literally stops the user in their tracks. They can't proceed further in the application. Like the login button just doesn't work.
Yeah.
Even with the right password. That's a showstopper. You can't use the app at all.
Right. Completely blocked.
And then there's the one teams really hate. Bug leakage. This means a bug was missed by the testing team entirely. It slipped through the cracks, got released into production, and then it's found by an end user or the customer out in the wild. It's a key measure of how effective the testing was, and obviously something everyone works hard to prevent.
Definitely want to avoid bug leakage. So, with potentially lots of bugs found, how do teams decide which ones get fixed first? Especially if resources are tight.
That's managed through defect triage. It's basically a sorting process. Teams prioritize defects based on things like risk, severity, how much effort it will take to fix, maybe business impact. It's usually a meeting involving key people, developers, testers, project managers, making those crucial decisions together about what gets fixed now, what might wait, what might not get fixed at all.
So a collaborative decision.
Very much so. And to measure how well they're doing at catching bugs before release, teams often track defect removal efficiency, or DRE. It's a metric. It shows how effective the development and testing process is at finding and fixing errors before the software goes out. The basic idea is number of bugs found and fixed internally divided by total number of bugs found both internally and externally after release. You want that percentage to be as high as possible.
A high DRE is good. Got it. Now, I've heard the term test fatigue used sometimes. Is that a real phenomenon in testing?
It absolutely is, and it's connected to something called the Pesticide Paradox. The idea is if you keep running the exact same set of tests over and over again, eventually they stop finding new bugs, just like pests become resistant to the same pesticide used repeatedly.
Ah, the tests lose their effectiveness.
Exactly. So to combat this, you need to regularly review your test cases, update them, add new ones, keep things fresh to maintain their bug-finding power.
Okay, interesting analogy.
There are also techniques like error seeding. This is kind of unusual. You deliberately introduce known specific errors into the code before testing begins. The goal isn't to test the code itself, but to evaluate how effective the testing process or the testers are at finding those known seeded bugs. It helps estimate detection rates.
So planting bugs to test the testers?
In a way, yeah. It contrasts with error guessing, which is much more common. That's where experienced testers use their intuition, their knowledge of common mistakes, to design test cases specifically targeting areas where they guess errors might be lurking.
Based on experience.
Exactly. And sometimes, organizations look for help finding bugs externally, right? Like putting out a call for assistance.
Yeah, I've heard of that.
That's the idea behind bug bounty programs. Organizations offer rewards, usually money, to individuals, often security researchers or ethical hackers, who find and responsibly report software vulnerabilities or bugs. It can be a really cost-effective way to get many eyes looking for problems, sort of augmenting the internal testing team.
Leveraging the crowd. It's really clear how vital all these defect management strategies and metrics are. They're crucial for actually delivering a high-quality product we can rely on. Without them, our digital world would be, well, much buggier. Okay, so we've got all these types of tests, all these ways to handle bugs. How do testers know when they've done enough testing? How do they measure that? And what about the tools that make this scale?
Right, the how much is enough question. That's where test coverage comes in. It's a metric. It measures the amount of the software that has actually been exercised or executed by a set of tests. It involves gathering data on which parts of the program ran, maybe which branches in conditional statements, like if-else, were taken, even down to which specific lines of code were hit. It gives you a quantitative feel for how thoroughly the software has been explored by your tests.
So it's about measuring what percentage of the code you've actually touched with tests.
Essentially, yes. And there are different ways to measure coverage, different levels of granularity. Statement coverage is one. It aims to ensure that every single executable statement in the source code has been run at least once by your tests. For example, if you have code like result A plus B, if result 0, print positive, else print negative, statement coverage would require tests that cause both the positive and negative print lines to execute.
Okay, hitting every line.
Pretty much. Then there's decision coverage, or branch coverage. This goes a bit deeper. It ensures that every decision point in the code, every if statement, every loop condition has been evaluated to both true and false by your tests. So for that if result 0 example, you'd need one test where result is positive, the if is true, and another where result is 0 or negative, the if is false.
Covering both outcomes of a decision.
Exactly. And then there's path coverage. This is usually the most thorough and also the hardest to achieve. It aims to verify that every possible independent route or path through a given piece of code has been executed. The number of paths can grow incredibly quickly, especially with loops and multiple conditions, so 100% path coverage is often impractical. But aiming for high path coverage on critical modules is valuable.
That sounds complex. It feels like there's a constant balancing act between doing tests manually versus automating them. When does automation really win out?
Yeah, that's a constant evaluation. Automated testing definitely has clear advantages in certain scenarios. It's much better for test cases that need to be run over and over again, maybe for long periods. Think regression testing. Checking that new code hasn't broken old features. That's perfect for automation. It's also pretty much essential for performance testing and load testing, where you need to simulate potentially thousands of users interacting with the system simultaneously. Humans just can't do that scale.
Right, sheer repetition and scale.
Exactly. Automation is also great if you need to precisely record the testing process, or if you have a very short time window for testing, automation can run much faster than manual testers. Also, executing tests in a very specific standard runtime environment. Automation ensures consistency. And frankly, as software gets deployed more frequently, maybe multiple times a day, manual testing for everything just becomes too slow and costly. Automation handles that speed.
So speed, consistency, scale.
Those are big ones. But the success of automation isn't just about doing it faster. It's measured by things like, does it find important defects? Defect detection ratio. How much time does it actually save? Execution time, overall time savings. Does it reduce labor costs or other costs? It needs to provide real value.
It's an investment. Are there ways to build testing right into the development process itself from the very beginning?
Oh yes, absolutely. A really well-known approach is test-driven development, or TDD. It's a methodology that flips the usual script. You actually write the test case first, before you write the functional code. The process is often called red-green refactor. Write a small test that fails, red. Write the minimum amount of code needed to make that test pass, green. Then clean up or refactor the code while ensuring the test still passes. It forces you to think about requirements and testability up front, and it builds quality in from the start.
Write the test first. That's fascinating. Really focuses on the requirements. So what about the specific tools, the environments testers work in? What's in their digital toolbox?
It's a huge toolbox. A key concept is the test bed. That refers to the entire environment set up for testing the specific hardware, software, network configuration, operating systems, maybe databases like PostgreSQL or MySQL, languages like PHP, frameworks like WordPress, everything needed to replicate the production environment or the target environment accurately.
The whole setup needed to run the tests.
Exactly. Sometimes you also hear about a test harness. This is often a collection of software, maybe stubs or drivers, and test data used specifically to test a program unit by running it under varying conditions like stress conditions or different data inputs and monitoring its behavior and outputs.
Okay. And specific automation tools.
Selenium is probably the most famous one for web automation. It lets you automate browser actions. It's powerful, open source, widely used. It does have some limitations traditionally that struggle with things like slash objects, and its API can be a bit complex for beginners. It primarily focuses just on web applications. Then you have tools like Sikuli. It takes a different approach, using image recognition to automate GUIs. This means it can automate basically anything you can see on the screen, including flash objects and even desktop applications, not just web apps. Its API is often considered simpler too, so different strengths.
Selenium for web, Sikuli more visual for anything on screen.
That's a decent summary. For managing tests, especially in Java environments, TestNG is a very popular framework. It's more advanced than older frameworks like JONIT, offering more flexibility, better reporting, and features like easily skipping tests. You can just set enabled false in the test annotation to skip a method or block.
Handy for temporarily disabling tests.
Very. And within Selenium, Selenium WebDriver is the core component for actually driving the browser. It provides the APIs for interacting with web elements. It also has features like taking screenshots. There's usually a take screenshot function, and a get screenshot method to capture the screen during a test, which is great for debugging failures.
See what went wrong.
Exactly. And for scaling up Selenium tests, there's Selenium Grid. This allows you to run your tests across multiple machines, multiple browsers, and multiple operating systems, all in parallel. It drastically cuts down the total execution time for a large test suite. Distributed testing.
Running tests everywhere at once.
Pretty much. And to make tests more maintainable, especially web tests, the concept of an object repository is important. It's basically a central place where you store the information about the UI elements your tests interact with their locators, like ID, name, XPath. Often these are kept in separate files, like property files. This separates the test logic from the element identifiers, so if the UI changes, you ideally only need to update the repository, not every single test script.
Makes tests less brittle.
That's the goal. Beyond the core testing tools, there are other related concepts too. You might have a modification request come in from the client. They want to change existing functionality. That triggers the whole cycle again. Development, testing, release. For planning any new work, project estimation is vital. Breaking work into tasks, allocating them, estimating the effort involved, and then validating those estimates. And for improving the entire development process, there are frameworks like SPICY Software Process Improvement and Capability Determination. It's a standard way to assess how mature and effective a team's development processes are, helping them identify areas for improvement.
Wow, okay. We have really journeyed from the foundational blueprints, the SDLC and STLC, through this incredible variety of testing techniques,
Yeah.
delved into the world of bugs and how they're managed, and now looked at the tools and coverage metrics that make it all feasible at scale. It's truly incredible to reflect on just how much intricate work goes into ensuring the quality of the software we interact with every single day, often completely taking it for granted.
Absolutely. Hopefully this deep dive leaves you not just, informed about the terms, but with a genuinely new appreciation for all that hidden effort. The meticulous work behind every stable app, every reliable website. It's pretty astounding when you peel back the layers.
Yeah.
And it's a constant evolving challenge for the people involved.
It really is. And that brings up a final thought to leave you with. Given this complexity, the constant evolution of software, how might the role of the human tester continue to transform, especially with the rise of even more sophisticated AI and ever smarter automated testing tools? What new frontiers are waiting in this ongoing quest for perfect software? Something to ponder. Thank you for joining us on this deep dive. We hope you enjoyed the journey into the world of software testing.